Hello everyone. Welcome you all for the last time to this course on social network analysis. So you may wonder what's the agenda of today's discussion. I have already concluded the course in the last lecture. So and we have already discussed the need of social network analysis in general. We have discussed the classical part of social network analysis, including the growth models and the old school statistics, etc. We have also discussed modern social network analysis, using deep learning to understand graphs in a better way, right? But whatever we have discussed so far, so you have heard, you have listened to me from an instructor's point of view, right? You may not have ideas about what a student thinks about this course. Of course, you have your own opinion in mind about this course, but I thought this would be an interesting idea to have a small discussion round with a set of students, right, who are actually working on social network analysis and may have better ideas than me about this course, about this topic in general. So today, I mean, we are going to have a very small kind of candid discussion, right? This is kind of a coffee with current types session, so it's not like that kind of thing, but we wanted to have it very candid so that you also understand from a student's point of view why this is an interesting topic, this is an interesting academic course, this is an interesting research topic, right? So it's my pleasure to introduce to you today's panelists. I would say, I mean, they are all my students, but for today's discussion they are all panelists. So I have with me three of my students. So they are PhD students working in my lab. So Shivani, you know Shivani. Shivani is the TA of this course. She is also one of the senior members of this of my lab. We have Karan. Karan is I would say a semi-senior kind of folk in the lab. He also works in graphs, so he'll talk about his work. Sara is another senior student in the lab. She's also a Prime Minister Fellow. She works in social network, I mean, in the intersection of social network and graphs in general. So, and this is going to be a very frank, very kind of candid discussion. Okay. So let me introduce today's panelists. Although they are my PhD students, but for today's discussion they are panelists. So you know Shivani. Shivani is the TA of this course. She is also the one of the senior members in the lab. She works in the intersection of natural language processing and graphs. Karan is another PhD student working in the lab. She is kind of a semi-senior, I would say, PhD student. She works in graphs, particularly deep learning for graphs. And Sara is another senior PhD student working in the lab, and she is also a Prime Minister Fellow. She works in the intersection of social network analysis and graph mining in general. So this is going to be a very frank, candid discussion just to understand students' perspective about the course and why this is an interesting, important research area, right? Although I kind of motivated you a lot that if you learn this course you would be able to to be interviewed by companies like Google, LinkedIn, right? Top notch companies working in social network, Facebook, Meta, Twitter, and so on. But let's hear it from the students, right? What they think about it. So let me start with Karan, right? So Karan, what do you think about this this course? Why you think that social network analysis or graph mining per se, right, is an interesting topic in today's arena, particularly in today's arena, where we see a huge amount of data available publicly, right? We can scrape data from Facebook, we can scrape data from Twitter, of course with some restrictions, right? Why do we think that this is important and people should pursue this as one of the career options?
Yeah, so this course specifically regarding social network analysis is very important. Let's say you have a lot of data, right? That's from Twitter. So there are many activities going on there. And for example, this hate speech and fake news, these are very prevalent terms in today's world. So we do want to address these challenges. For that, we need a network analysis, right? and that has some properties and some algorithms that have been discussed in this course. So we do want to put our focus on these specific nuances and details so that we can address these challenges. And for example, right, you discussed about the network properties like degree centrality, articulation points, and similarly, if I talk about a large level perspective, let us talk about community detection. People form echo chambers also there. So we do want to identify these things. So for that, we need to learn these techniques first.
So I mean that's very good. So but can you tell us very briefly about your research? What's the research area that you are currently working in?
Okay, so I work on algorithmic side of graphs, that is graph representation learning. So in that, our aim is to learn embeddings that can represent nodes in a graph in a vector space. So essentially, what we do, we conduct amalgamation of deep learning and graphs so that we can devise new algorithms that can operate specifically on graph structure data. So to perform successfully and tasks like node prediction, node classification, edge prediction, graph classification, etc., maybe community detection, and so on. So I work generally in this domain. Yeah.
Yeah. So basically that you mentioned, so this graph representation learning, is it like similar to normal representation learning in general?
Okay. Yeah, it has same notion of achieving and doing the things. But if you see, graphs are very difficult and exciting to handle than other type of data.
Right.
Let's say graphs are not sequential in nature, right? The other type of data you have, let's say you have frames in a video, maybe you have pixels in an image, or sentences in a paragraph, or words in a sentence. So graphs are not sequential there. So they have very specific property of isomorphism that are only specific to graphs.
Okay.
And also, the one thing that is very specific to graphs is that you can increase the complexity of the data enormously just by adding the number of edges between already existing data points, that is nodes. You keep them fixed. So that is not the case you observe with images, videos, or text.
So just to interrupt here, audience, if you remember, I exactly mentioned this point in the graph representation learning chapter, that why graph representation learning is different from, say, language representation learning, right? What's the challenge in graphs, right? We discussed that unlike say a speech, right, or a text where you have a sequential data available, right? You know that okay, the word, say, I am a boy, the word am is at the second position, right, in the particular sentence. In the graph, there is no such notion of position, right, of a node in the graph, right? So and Karan rightly mentioned, and this is one of the emerging areas that's going there in the research community, right from the static graph, temporal graph, heterogeneous graph, right, attributed graph. You have plenty of information. How do you inject all this information? How do you incorporate them together to come up with better representation for the downstream task? Now the downstream task can be, it can, the representation can be task dependent, the representations can also be task independent, right? And as Karan mentioned, I think one of the major focus of his research is to learn the representation, right, in an appropriate manner, particularly in the temporal setting. Okay.
So you talked about graph as a data structure being unique. Then how do you incorporate these unique properties and network metrics into designing your graph representation learning algorithms?
Okay. So you're essentially trying to ask that, okay, how are these network properties or measures important in designing the graph representation learning?
Definitely.
Okay. So if you see, right, most of the graph representation learning algorithms that have been developed in the past few years, they focus mainly on neighborhood aggregation. They're based around that. So unlike, right, deep learning architectures or models, whatever you say, so these are not like here we can't go on keep on increasing the layers, because in the end we will end up learning nearly the same representation for every node in the graph. So it is how it is different. So here we need to focus on this thing. So now what will happen is we learn same representation. Now a network property is responsible for this, and that property is small world property. So if we already know that, okay, small world property, you can reach every node in the graph from any particular node in 4 to 6 steps. So you won't be increasing the number of layers too much, and then just say, okay, my algorithm is performing poor. So that's why it is important. I'll give you another example from a real world dataset that we worked on. So we have a dataset where the end task was to do node classification. So and we ran standard algorithms like graph convolutional network, graph sage, and graph attention networks, and they performed miserably, and we were surprised. So then we dug up the issue, and we found that there was no homophily in the network. So yeah, we should care about the different network properties and measures and other techniques while designing and also utilizing these algorithms. And I think they have been discussed in this course very well.
So again, I hope you have understood some of the terminologies, if not the entire discussion, but at least you have you have rightly pointed out the terms like homophily and all these stuff, right? That we have discussed in the course, right? Thanks, Karan. So let me now move to Sarah. So Sarah, tell us briefly about your research, your research interest, your research work in general.
Sure. So if we look at the world around us, as we were discussing earlier, it can be mapped in terms of various entities that are interacting with each other, and these interactions are very dynamic in nature. Similar thing happens when you look at the online world, where you have various heterogeneous entities, like you have users, you have products, you have content, and all of these entities are interacting with each other. And my area of research, which is called social computing, aims to understanding these various interactions and trying to unearth properties of these interaction, as well as what can be done once we understand these interactions. So my area of research, which is social computing, within that I work specifically in the area of analyzing the networks for hate speech detection as well as diffusion.
Okay, so I have one question.
Yeah.
So I'm just trying to relate my work with yours. So I think we can use graph representation learning techniques, maybe let's say you mentioned hate speech, to identify hate speech users or fraudulent users from some benign ones. Can we use that?
Yes, definitely. So see, once we are able to map these user interaction networks in a form of a graph, then we can run all sort of graph representation learning algorithms on top of that, and the embeddings that we obtain from this, then we can use it for various downstream tasks, as you were mentioning. One of them would be like classifying a user as benign or harmful, or maybe you want to detect whether a user is a bot user or a genuine user. And not only that, not only like specific to just classifying the network embedding, we have personally observed in our research that when you combine these network embedding along with, let's say, the textual embeddings of a post, you can improve the performance of hate speech detection algorithms. And this goes back to the property of homophily, where we know that people who are more likely to interact with other hateful users are likely to also post hateful content.
So all the tasks that you just mentioned, they are essentially, classification or detection tasks, right? But can we use this user interaction networks to go beyond classification and perform like more complex tasks maybe in the network?
Yes. Definitely we can do that. Like at the end of the day, everything boils down to classifying a user or a content into some category. But networks are useful for not just categorizing specific groups or of users or entities. We have studied in this course specifically that networks are also useful for understanding how the information is spreading among these various entities. So the concept of cascade and information diffusion can be studied by understanding these user interactions. And take the example of fake news. We know that it goes viral very easily. So if you have understood, okay, these are the central nodes in my network, and you know that they are more likely to spread fake news, then you can develop your intervention strategies in a manner that prevents the spread of this fake news. So understanding diffusion through networks is another area of research.
So thanks Sarah. So I mean, if we summarize the discussion of Sarah's research, so Sarah mostly focuses on understanding a particular offensive content, which is hate speech, and how we detect it, how we stop the spread of hate speech. Can we come up with different intervention strategies to combat online hate speech in general, right? Now let me move to Shivani. Shivani's work is very interesting. She works in the intersection of NLP and I mean mostly NLP, but her research also needs a lots of technique from graphs, right? Now I motivated you in one of the chapters that the graph by itself. I mean, if you think of graph, I mean one can assume that this is basically a theoretical domain, right? It has less practical application, but it has a lot of places where you can use graphs in different applications. One of these applications is language technology, natural language processing. So let me ask Shivani. So can you briefly tell us about your research and why you feel that you felt that graph could be one of the components of your research?
So yeah, so basically my research domain is about analyzing the discourse between different speakers, right? So I work in the area of this dialogue analysis and identifying and explaining the different aspects of the dialogue, like emotions and sarcasm and profiling different speakers, right? So when we talk about graphs, so basically graphs requires some kind of nodes and some kind of relationship between the nodes for the edges to form, right? So in the terms of dialogue, so what we have as an input is basically a sequence of utterances which are uttered by various different speakers. So now these speakers and these utterances, they basically exist with some kind of relationship among each others. So the speakers might have some different kind of relationship among others, and the utterances can have some other kind of relationship with each other. For instance, like a simple relationship can be a temporal relationship, that is one utterance is occurring after the another utterance. So we can exploit these relationships and can explain or can present these dialogue input as the form of graph, and then as we just discussed, can use the existing graph representation methods or other techniques that we have studied in this course to basically analyze the structure and then use it for the end task NLP task like sentiment classification and so on.
I had a question. So you talked about the concept of utterances,
Right.
but where they have relationships. What about applying the concept of graphs in tasks that do not have these relationship explicitly present?
Right. Okay. Yeah, so I think what you're trying to ask is like, can we apply graph structure to standalone text, like say movie reviews or tweets, right? So yeah, so definitely we can, because natural language itself, the words that are present in the natural language, they often occur with some kind of relationship with each other. So these words in a sentence, they can have like a syntactical relationship which can arise from the grammar of the language, or they can have a semantic relationship, for instance, like the relationship between the POS tags of the different words in the sentence. So then in NLP, we have different kinds of parser, which basically, takes as input the input sentence and then results in a network of this syntactic and semantic relations. So the output of this parser, or the graph or the network structure that we get from this parser, then again, this graph can be used as a separate feature or itself to, again, like perform the task that we just mentioned, like sentiment classification or sarcasm detection and so on. So yeah, so we can use this graph structure for standalone text as well.
Okay, I have just one question. So I think we can use graphs, right, as a source of external knowledge for NLP tasks because they can add a lot to the information pool already out there.
Correct.
So will you be able to share your views on that?
Yeah, sure. So I guess you're talking about knowledge graphs, right?
Yeah.
Yeah. So area of knowledge graphs and using those in NLP tasks, it is basically an area that is currently being well explored in the NLP domain, because let us just understand it intuitively. So for example, if we are talking and you mention, say, like you admire the work of Leonardo da Vinci, then me as I should be aware like who Leonardo da Vinci is, or maybe some of his works, to understand your statement clearly, right? So same goes for say online dialogue agents, right? So if you are talking to a chatbot and you mention the same thing, that you admire the work of Leonardo da Vinci, then the chatbot must also should have some kind of background knowledge or some kind of context about who Leonardo da Vinci is, or what are his works. So yeah, so for incorporating this kind of knowledge, for that knowledge graph such as ConceptNet, or for incorporating some kind of common sense knowledge, so concept graphs such as Comet, they are basically, they can be used for NLP tasks to incorporate these knowledge and can answer your the end task, whatever you want to see.
So they will essentially help us in lifelong learning, right? I think.
Yeah, basically. So we learn with our experience. So see, we cannot give such a long time to the machines, right? So to just to provide the background knowledge beforehand to the machine. So for that, knowledge graphs can be helpful.
So I mean, if you have noticed, so she has mentioned a terminology called knowledge graph. Although I think I did not mention this term in the course, but we discussed a related terminology which was heterogeneous graph, or something like that. So if you think of knowledge graph, is basically, I mean, you can think of it as, you can easily define it using a tuple. You have two objects, and two objects are connected through a relation, right? And that object, these two objects, right? They can have their own properties. This relation can also have its own property, right? For example, say there is a huge knowledge graph, and there are two nodes, two entities in the knowledge graph. One is Barack Obama, another is the US. And the relation is was president, right? Or this knowledge graph, there is India as an entity and Narendra Modi is another entity, and the relation is prime minister, right? And something like that. So you can think of this huge knowledge, right, in terms of graphs, and then you can you can run whole bunch of state of the art again representational learning techniques to understand, to represent relations, to represent nodes, and so on and so forth for different tasks. So let me ask a few more questions, right? So since you have particularly Shivani and Sara, since you have already faced many interviews, right? What kind of questions are generally asked, and what's the expectation, right? And I mean, what kind of things people actually expect from a student to have at this moment about say let's say you are posing yourself as a graph learning research, researcher working in graphs, right? So what kind of expertise people generally expect from a candidate, from a student? What do you think, Sara?
So one of the interesting things about studying social network analysis is that it covers a wide range of topics. So you get to learn about statistical methods. So you have to improve your understanding of that. At the same time, you have the other spectrum of graph representation learning, where you have to have background knowledge of deep learning systems. Apart from that, when we are analyzing graph, we are using some libraries that we don't usually use. For example, in Python, we work extensively on network X. So it gives you a wide range of what you can say knowledge and expertise in one particular course. For example, in my interviews, I've seen that when we talk about having a background knowledge in graph learning, they expect us to be proficient with both deep learning as well as hands-on in libraries like network X.
Yeah.
So that is what I have observed that they expect us to know.
Okay. What do you think, Shivani?
Yeah. So, especially if you talk about the NLP domain and stuff. So, basically, with the boom of this social networks and all, so many companies or many interviewers, they expect you to have some kind of knowledge about the about how information spread throughout these networks, so that if the interviewer, they deal with these kinds of networks. So yeah, they have that kind of expectation. And as Sarah correctly mentioned, that the knowledge of statistical graph representation, as well as this deep learning knowledge, that how you can basically exploit this graph representation that we have to perform some kind of end task. So that is some kind of knowledge that the interviewers, they expect nowadays that we must have, because essentially all the data can be expressed as a form of graph, and then the methods can be used over that.
So, so what I understood is that hands-on experience is of course needed. You should be an excellent coder, right, to be able to crack these interviews, to be able to say deal with large scale networks. At the same time, you should also have a decent knowledge, about the theoretical understanding of all these techniques, right? So guys, be careful. So whatever techniques I have discussed so far, particularly in the network growth models and graph learning models, you should be able to understand those techniques properly. If the video was not sufficient, if you think that the video is not sufficient, you just look at the original papers, right? For example, the Node to Wake paper, or the deep work paper, or the GCN paper, right, to understand things thoroughly. That's very important. Don't think that just take something, import a library, run it, right, throw some results, and the reviewers will be, the interviewers will be impressed with the results, right? Of course, hands-on experience is needed. So thanks guys, thanks a lot for the comments. I think this was really helpful to our audience, particularly students and practitioners who are still thinking about whether this is a really an interesting area to explore further. And I also again like to thank all the listeners, all my audience who have gone through this long journey, right, of 12 weeks, and hopefully have understood most of the concepts that we have discussed. As I mentioned, I mean, if you are really interested to work on this topic, there are multiple publicly available sources from which you can get data, you can get codes, right? Just run it, see the results. If you think that improvement is possible, build your own model and try to improve it, and if possible, publish it in a good venue. Okay, there are top venues in this area, conferences like SIG-KDD, World Wide Web, right, ICDM, NeurIPS, and AAAI, ICHKAI. These are top conferences where people publish their good work, right? Strongly encouraging you guys to focus on those venues, read state-of-the-art research, and update your skills. Okay, and hopefully we will meet some other time to discuss further about this particular area, this kind of exciting area. And you feel free to reach out to me with, using my email ID and my other social media handles. Thank you very much.